Okay, so this will cover sequences and series. We had two main types, arithmetic, which is when you have a pattern where you're adding a constant, or we call that a D for the difference. And then geometric, which is more, it looks like multiplication by a common ratio that we will call R. So first off, there's a bunch of formulas. We'll kind of be using these throughout, but just briefly to run down the ones given. The first one in the top left there is going to be for an infinite series for certain geometrics that we'll talk about. Basically, one little trick to remember the difference, I guess, if you see an R in the formula, that's going to go with the geometric. So these three go with geometrics, and then the other ones are going to go with arithmetic. And a little trick on those two, I guess the ones that have a plus sign in there are going to be the arithmetic ones. So just kind of continuing to talk about what they do briefly. This one's going to be for an infinite series, which is a sum of a bunch of terms. The other geometric ones, this one down here is just for an explicit formula, just to find a certain term. And the last one is for a series, which again is the sum of terms, but it's for a one that's not infinite. It's just, it has n terms. Okay, and then the other ones for arithmetic, this one right here will get you the explicit formula, which will again find any given term. And the other one here is going to give us the sum of a bunch of terms, or a series formula. Okay, so we'll see them in action. So here's our first situation here. Let's say we are training for a marathon. We're going to run 0.5 miles on day one, and then we want to basically add 10%. So be careful, even though we're adding 10%, it's really a multiplication problem, because to add 10%, you would multiply by 1.1. So that's going to turn out to be the common ratio, or the R value here. So the sequence, of course, we would start with 0.5. That's day one. And then if you were to just multiply that by 1.1, you see it adds 10%. And continuing that out, there are the first 5 terms. Okay, this one is geometric because of that pattern. The pattern involves multiplication. So it has that common ratio of 1.1. Okay, let's state an explicit formula. So explicit formula, just kind of go back to what is the pattern. And I kind of think about it again, we're starting with 0.5, and what we're really doing to that is we are multiplying by 1.1 over and over and over. So that should kind of lead you to the explicit formula. It's just going to be the 0.5 initial value times that 1.1, and the exponent on it is n minus 1. And just to kind of think about that is, if you think about when you go and get, let's say, for example, the third term here, you're really starting with the 0.5, and you are multiplying by 1.1 only twice. So that's why the exponent is actually one fewer than the term number. So hopefully that'll help remember that. Recursive now, so when you do something recursively, it's just to kind of get a term if you know the previous term. So real quick on that, for recursion, the idea is, again, if you have a bunch of terms, let's say there's a term here, 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 and let's just say this one is the A, let's say that one's the nth term. The idea is the term right before that would just be the n minus 1 term. It would be one fewer the term previous. Or you could also think of the following term as being the n plus 1 term. So we kind of use that notation a little bit in the recursive formulas. And basically what we're going to do, we're going to have 2 ways to say it. You can either think of it as, if you look at the first formula there, so a sub n, again, is this term right here, right? And the way you would get that term is by taking the term before it, and it gets multiplied by 1.1. So that's what this is saying right here. Okay. Or you could think of it, there's kind of 2 ways you could say, all right, if I want to write a formula for the n plus 1 term, that would involve the a sub n term times 1.1. Okay, so it's just a way of using the term right before the one you want, and in this case we're just multiplying it by 1.1. Okay, so how many miles, if this pattern were to continue, the long sequence that we wrote in part A, if that continued out to day 30, how many miles would you run on that specific day? So we're just going to use the formula. Ooh, cool colors there. We're just going to change the n to 30 and use the formula that's in part C. okay, the explicit formula. And we're just going to take 0.5 times 1.1 to the 29th power, and just be careful, use your order of operations in the calculator, and you should get 7.93 miles. Okay, so that's what would be the 30th number in our pattern. Okay. All right. On what day will you run more than 50 miles for the first time? So this one you got to think about. I'm saying again, if the original sequence, if it continued really far, how many days would it take for this number to get to 50 or higher? Okay, so there's a couple ways to do this. One way is you can kind of just do a little guess and check. Okay, where basically 50 becomes the term, becomes the a sub n basically, and we need to figure out what n that would be. So some people might want to just try plugging in values for n. That's totally fine. One thing that I actually did that might help for this problem, because we haven't really talked about how to solve when the variable is an exponent. If you guys are familiar with logarithms, you can solve it. But at this point, we haven't talked about that yet in the Algebra 2 course, at least at this year right now. So what I suggest doing is maybe even go to your calculator. And what I did was I put in Y1, this is just the explicit formula, which we used as part C. Okay, I'll talk about what's in Y2 in a second. I put that formula in, and then if I go to the table, if you notice Y1 there, all these blue numbers, this is the sequence. Like, this is just a way, I mean, you could have done part A this way, list the first 5 terms, there they are. And what I want to do is just basically see or scroll through this list and see how long does it take for that number. Again, these numbers in blue are the number of miles you run on a given day. That is the sequence. So I want to see how long does it take for that thing to get up to 50. And you might think it's going to take forever, but it's actually growing a little quicker as we go. It's not going to take too long. I believe it takes about 50 days based on doing the equation. But this is just an option again. So we see we're getting close. Yeah, so on the 50th day, this person finally ran more than 50 miles. Okay, that's not the sum. I actually have the sum of the values, you know, the cumulative sum. I have a formula in Y2 to find that we'll talk about in just a second. But on day 50, you would actually have to run 53 miles, which again is probably unreasonable, but if the pattern continued, that's what it would take. So that's what we're looking for in part F. And again, the way I found that was just plugging in the explicit formula into Y1. Okay. So we end up getting n is 50. Okay, 50th day there. Okay, how many total miles now? Okay, so this is going to be the sum. So we have the formula. This is again geometric. So the formula, if you want to just do it using the straight formula, it was the A1 times 1 minus r to the n all over 1 minus r. Okay, so again, it's a geometric series. We know n is 30. A1, of course, was 0.5, and the r value in this problem was 1.1. So you could go ahead and do that with the formula there. Another way to do that one using the calculator too, if you notice what I put in Y2 here, is that formula that I just used. A1 times 1 minus r to the x all over 1 minus r. So what Y2 was going to show me, these red numbers here, these are the sum or the cumulative amount ran where x is the number of days. Okay, so we were talking about 30 days. If you kind of notice right here, this is going to verify that the sum was around 82.247. So just be clear on the numbers. The 7.9 is how much you ran on that single day. The 82 is the total number combined. Everything previous, you know, added together. Okay. There's actually one other way you could do the sum problems if you want to, using sigma notation. So I'll just show that real quick. If you want to use sigma notation, you can go into your math, and then you scroll towards the bottom of this list. There's a summation. Okay, and we always start with x equaling 1. In this case, we're going up through 30 terms. And then in here, we're going to put in the explicit formula for the sequence, which was 0.5 times 1.1 to the x minus 1 power. And that's going to go ahead and give us the same answer that we got two other ways. Okay, so a few options there. Okay, so that was a geometric situation because we were multiplying. Okay, your other option, another problem here. Let's say you're training for a marathon. You're going to run 0.25 miles the first day, and you're going to increase the distance by 0.5. So you're going to add 0.5 to your distance each day. Okay, so since we are adding a constant amount, that's going to be arithmetic. So first off, let's get some of the terms here. First 5 terms of this pattern. Of course, we're going to start with 0.25, and we are going to simply add 0.5 over and over and over. Okay, so that would be the first 5 terms. Okay, so which type of sequence would this be? Since it's, again, since it's adding a constant, it's arithmetic. There's a common difference of 0.5, so that'd be a good explanation. Say something about adding a constant amount. Okay, so now how many will we run on day 30? Okay, so we can think about getting ourselves a formula here, and let's kind of derive the formula again. So think about the pattern. We're starting with 0.25, and we are adding, right? So a general formula for the nth term would be exactly that. Start with 0.25. We are adding 0.5. But just keep in mind again, for example, for the third term, for example, we only added the 0.5 twice. So you only add the 0.5 n minus 1 times. Okay, so that's kind of your general formula, which was an equals first term plus common difference. Okay. So that's going to get us our answer to part C. Okay, so we plug all that in. I'm getting around 14.75. Okay, and a way to kind of verify this too, if, again, using the graphing calculator, if you go ahead and enter, let's see, this right here into your y equals and just use the x where the n is, you can get a little table and just kind of, use that to guide things. So that is right here. This is actually the explicit formula for the sequence. I'm going to use y2 a little bit later. Again, it's going to give us the sum, so we'll talk about that in a minute. But what you can do is if you take a look at the table, you will see again the y1, the blue numbers there, that is just how many miles you run on the x day. Okay, and the question we just answered was asking about day 30. So if we just scroll down a little bit here to 30, you'll see we'll get the 14.75. Okay, so there it is right there. Okay. All right, so what else we got here? Find the total number that we run on the first 30 days. Okay, so this is a combined total. On days 1 through 30, how many miles total will we have run? So this is where we're going to use the series formula, n over 2 times a1 plus an. So again, a1 was 0.25. Now just remember here, be careful. That number is how much we ran on the 30th day. Okay, it's tempting, and a lot of people want to put 30 there, but the formula is actually a sub n for that term right there, not just n. So n is 30 here, but the 30th term is 14.75. And that has to deal with, this formula comes from when we pair up the terms. We kind of talked about in class, the first term plus the last term, and we have a certain number of pairs and all that stuff. So if you remember that formula. But that gets us 225. What you can also do, let me just jump aside real quick. The formula that I just used was this. Okay, but what actually happens is sometimes you don't know this term. Like let's say we wanted the sum of 100 terms and we don't have the 100th term to use. What I use is the fact that this is really the same as a1 plus d times n minus 1. So what I can do is rewrite this formula, okay, substituting in all of this Okay, so make sure we see the connection here. That is the same as that, right? So I just kind of combined two formulas into one in a way. And then if you just do a little quick simplifying, there's A1, there's another A1. So you really have two A1s plus D times N minus 1. This is kind of another shortcut way to find the sum. If you don't know that last term, you don't need it. Okay, the only things we need are the first term and the common difference. Okay, so it's kind of nice, just an alternate version, and that formula may or may not be provided. You will definitely be given this one and this one to use. So you can always combine the two to get the new one. But what I did, I went ahead and plugged this into Y2 on my calculator for another way to get the sum. So I'll show you what that looks like. In Y2 here, I just used, here you can see the x over 2 part. There's two A1s plus D times x minus 1. So this will now give me the total sum of the distances ran through x days. So for example, in the table, we just answered the one question was saying on day 30, we ran 14.75 miles. But after day 30, the combined total, all this stuff added together would add up to 225, and that is the answer to our part D here. 225, if you take a look where we just were, yeah, using the formula, we get 225 as well right there. Okay, this one could be done with sigma notation as well, but I'm not going to spend the time right now. Okay, so this one now, the calculator is going to be really helpful. Okay, so imagine you're running these distances, right? You run 0.25, then 0.75. On what day will you reach a total of 26.2 miles? So you're going to have to take the 26.2 and plug it in. That is the sum. Okay, the thing that's unknown here is the n value. Okay, so you're either going to have to solve a messy equation, okay, using some algebra, distribute, and it actually will turn into a quadratic because you have n's right here, and you have an n there and there. So it gets a little bit messy. So if you have the equation in your calculator, and you can just go right to the table and say, all right, I'm looking at the red numbers because that's the sum, that's the combined sum. I want to know when does that get to 26.2. It's going to make this problem so much easier. So you can kind of see on after day 10, you've run 25 miles. After day 11, you've run a total of 30.25. This is combined. So somewhere in between those two, somewhere after the 10th day, so on day 11, that's when you would have run your 26.2 miles. Again, this is combined sum. It happens sometime around day 11. Okay, and if you solve the equation using quadratic, hopefully, one of your answers would have been 11. Okay, all right, one other problem. So let's say you plan to read a book, 675 total pages, and you want to read one page more each day than you did the previous day. Okay, you want to finish the book in 30 days. How many pages should you be reading on day 1? Okay, so this is definitely a sum problem, a series. It is actually arithmetic because of the pattern. You're reading one page more than you did the day before. So for example, if you read 6 pages one day, the next day you have to read 7, then 8, then 9. So it is an arithmetic sequence. The D value here is 1. That's the pattern. Okay, so if we plug everything into the formula we just used to find the sum for arithmetic, 675 is the sum. That needs to equal n over 2. Well, n is 30. It's going to take 2 days, or 30 days, I'm sorry. N over 2, 2 times A1 plus B times n minus 1. So you really just have yourselves an algebra equation, which is definitely solvable. If we take a look, we can solve that. So let's do some algebra here. So 675, the 30 over 2 is really 15. Okay, this is going to be 1 times 29, right? So I would first divide both sides by 15. Just make it a little easier on yourself. 45 equals 2A1 plus 1 times 29 is just 29. Okay, and now just subtract the 29 over. You're going to get 16 equals 2A1. which means A1 must equal 8. So you'd have to read 8 pages on day 1 to make this thing work out. Okay, so it's going to be something like 8, then day 2 you'd read 9, then 10. If you did that for 30 days, if you had 30 terms here, okay, the sum would equal to 675. Okay, so that's kind of what we just found. 8 plus 9 plus 10 plus 11 all the way up. All right. Okay, and one final little topic here, the old infinite series. So imagine a string of numbers that actually goes on forever, okay? Can we get a sum of that? So it might seem, like how in the world would, if you add up an infinite amount of numbers, how could that ever just not add up to infinity? So the issue is something like this. If we take a look here, here's a pattern. It looks like our sequence is actually arithmetic because it looks like we are just increasing each number by 2. If we were to add that up, and again, this thing's going to go on forever, infinitely long. So we would be adding 12, then 14, then 16, then 18, and just forever. So you're right. If you just keep adding bigger and bigger things, this thing actually is going to go to infinity. The fancy name for that is this sequence would diverge because it does not come to a real number. It just grows infinitely with no upper bound. Okay, and actually any arithmetic sequence, okay, all arithmetic, I'm going to call them series because we are adding them up, all of them will diverge. If it's arithmetic, it goes to infinity, or it goes to negative infinity, diverges. Okay, what about geometric? Okay, here's an example. If you look at our pattern, this looks like there's a common ratio of 2 that we would continue to add over and over and over. Okay, 4 plus 8 plus 16 plus 32 plus 64 goes on forever. The terms are growing and growing and growing, no bound. This is very similar to what just happened in A. This thing would diverge as well. So that one's a geometric series. And note, the R value was 2, right? Okay. So here's our last case. What if these terms are 4, then 2, then 1, then 1/2, and so on? In this case, the terms are actually getting smaller because our ratio is 0.5. Okay. So in the long run, these terms are going to get smaller and smaller and smaller and smaller and smaller. So eventually, if you think when we're way out far in the end, the amount that we're adding is really not having much of an impact. So the funny thing is this thing actually will converge to a real number. There will be a sum here. So one little definition before we find the number. It will converge to a real number. Okay, and the rule, that happens when the terms get smaller and smaller like that. And that will happen if your sequence is geometric and the R value is between -1 and 1. Okay, so this one is that case, right? The R value here was 0.5, so this meets the condition. So there was one extra formula. The sum for an infinite series is always A1 over 1 minus R. Okay, and it actually comes from the other geometric series formula that has the other one, has a term in here, 1 minus R to the n or whatever. That term just kind of goes away when n becomes infinity. So notice they are the same formula though, other than that. So just to get our final answer here, we are just going to take our first term of 4 over 1 minus the ratio, 0.5. So we have 4 over 0.5. And 4 divided by 1/2 should get us an 8. So this big string of numbers, this infinitely long string of numbers, again, it goes on forever. It really would just add up to 8. So it seems impossible to have an infinite number of things add up to a number like that, but it really does. So that covers the infinite series. And that covers all this stuff. So we did our geometric, we did our arithmetic, we did series and sequences, and that is it.